Just like we could for exact linear models, we can give interpretations to the slope and intercept of a regression line. However, there are some complexities that come up when we're looking at an approximate relationship. So our slope is the number a from the calculator readout. We rounded that to 4 decimal places. So our slope is negative 0.0046 after rounding. The interpretation we'll give is, so every time x increases by 1, so that means for every additional 1 pound of weight, okay, so for every time x increases by 1, the model predicts that y, so in this case, the gas mileage, the slope is negative, so we predict the gas mileage will decrease by 0.0046 miles per gallon on average. And notice that we don't write in the negative sign because we have already said it decreases. So we don't have a negative sign when we're stating our interpretation. We said the word decrease, and that told us that the slope was negative. Okay, so that's the slope. How do we interpret the intercept? So our y-intercept is at 0, 34.7359. What would the interpretation of that y-intercept be? Well, it says that when x is 0, x is the weight of the car. When the car weighs 0 pounds, okay, that sounds weird, but let's finish the sentence. The model predicts, because we're still talking about what the model does, the model predicts a y value of 34.7359. So the y value is the gas mileage. So the model predicts gas mileage of 34.7359 miles per gallon. Okay, so we can write that down. But that really doesn't make any sense, right? The problem is this bit about a car that weighs 0 pounds. Is there any such thing as a car that weighs 0 pounds? No, not even close. A car can't weigh 0 pounds. It can't weigh like 0.01 pounds, so it can't get really close to weighing 0 pounds. Cars are real heavy. So talking about what happens when a car weighs 0 pounds doesn't make any sense because that's not a thing that cars can do. Often, when we're working with a regression model, we'll get a y-intercept that just doesn't mean anything. Sometimes it does, sometimes it doesn't. We can always write down an interpretation, but sometimes that interpretation is going to be nonsense. The other thing to be aware of is we can always interpret the slope. There will always be an interpretation of the slope that makes sense. However, we have to be careful with that too. Notice that we didn't say that if we add 1 pound to the weight of the car, that will decrease the car's gas mileage by 0.0046 miles per gallon. We're not saying that this model predicts that if we put a 5-gallon jug of water that weighs 40 pounds in the back of our car, we can multiply it by that number to figure out how much the gas mileage decreases. We're not saying that an increase in weight causes the change in fuel efficiency. What we're saying is that we predict that a heavier car will be less fuel efficient. We predict that a heavier car will have additional properties that are different from the properties of a lighter car, and those properties might also affect fuel efficiency. Very often we'll have linearly related values, but there isn't really a causal link between them. One example is you can get a linear correlation between how tall a child is and how well they can read. But that doesn't mean that if you have a child stand on a stool, they're going to read better. Right? The reason that the taller children can read better is that they're typically older and have been like going to school for longer and have learned how to read better. It's not necessarily the case that changing the value of the explanatory variable will cause a change in the response variable. So we have to be a little bit careful when we're interpreting the slope, not to use any language that implies that changing one value causes a change in the other. Before we leave interpretation behind, let's also talk really briefly about these R squared and R values. If we were in a semester-long statistics class, we would spend a bunch of time talking about R squared and R. Your calculator may or may not be displaying them. If your calculator is not displaying them and you'd like it to, you can go into the mode screen, scroll down and find stat diagnostics, and turn it on. Now, if your calculator is displaying R squared and R and you don't want it to, you can also turn stat diagnostics off. In general, R squared and R are measures of how well the regression equation fits the data. If R is close to 1 or to -1, so if the absolute value of R is close to 1, that means the equation is a better fit for the data. If R is exactly 1, that means that we have a perfectly linear relationship and we're real happy. On the other hand, if the absolute value of R is close to 0, so that means it's either a very small positive number or a very small negative number, then the equation is not a very good fit for the data. However, it's important to be cautious about these R squared and R values, because while they can tell us whether a linear equation is a good fit, they cannot tell us whether a linear equation was the best choice for a fit. We're going to meet different kinds of equations, quadratic, exponential, and logarithmic, but we can also fit to data. And it is not correct to just try all 4 kinds of fit and pick the one that gives you the biggest R value. In order to decide what kind of equation to use, we need to look at what we know about the situation, the actual pattern of the data, what the graph looks like. Does the graph look like it's a good fit for the scatter plot? We really need to think about what intuitively does our data set actually look like in order to decide what is the correct kind of equation to fit to our data.